Now some questions from the exercises. The first type of question is, arrange the following compounds in the increasing order of their property as indicated. Now first compound is acetaldehyde, then acetone, di-tertiary butyl ketone, methyl tertiary butyl ketone. Now this compound is di-tertiary butyl ketone. This is methyl tertiary butyl ketone. This is acetone, and this is acetaldehyde. Now here we are having two bulky tertiary butyl groups, and the tertiary butyl group is having a higher magnitude of inductive effects plus psi effects. So all these factors, the higher magnitude of plus psi effect diminishes the partial positive charge over carbon to a greater extent, and then the bulky tertiary butyl groups inhibits the entry of the nucleophile. So steric inhibition is occurring at a larger extent in the case of di-tertiary butyl ketone. Now the steric hindrance here is slightly decreased because there is only one tertiary butyl group, the other is a comparatively small group, that is methyl group. So the steric hindrance is lesser than this one, and again the plus psi effect of this tertiary butyl group is larger, but the plus psi effect of methyl is slightly less. So here charge neutralization, diminishing of charge is lesser than in this case, and again steric hindrance is lesser than in this case. Now here we are having comparatively small methyl groups, comparatively small plus psi effect. So this carbon will be having a slightly higher partial positive charge than this carbon. So this is easily attacked by a nucleophile than this one. And in the case of acetaldehyde, the inductive effect of hydrogen is practically nil, zero. So only methyl group with a small high effect compared to the bulky tertiary butyl groups. And the steric effect is also smaller because there is only a small methyl group. So the order is this one. The acetaldehyde molecule having high reactivity, the highest reactivity among the four compounds, and di-tertiary butyl ketone having the least reactivity. Now give simple tests to distinguish between the following pairs: propanol and propanone. Propanol is propionaldehyde, CH3 CH2 CHO, and propanone is CH3 CO CH3. Now propanol is an aldehyde and it can reduce tolerance reagent to metallic silver, and it is observed as a mirror inside the test tube, silver coating inside the test tube, and when we view from the outside of the test tube, it will be observed as a mirror. So it is called a silver mirror, and tolerance reagent is ammoniacal silver nitrate. It is a complex compound. The reaction between an aldehyde and ammoniacal silver nitrate we have seen earlier. Now aldehyde can give a tolerance reagent test, and again aliphatic aldehydes can reduce swelling solution to red cuprous oxide. Failing solution may be considered as a solution of cupric oxide. It is reduced to Cu2 or cuprous oxide, which is having a red color. Now these two reactions are not given by propanone, that is acetone, but acetone contains a CH3CO group, So one CH3CO group is present in acetone or propanone, and such compounds can react with iodine and alkali to give a yellow precipitate of iodoform CHI3. So that is how we distinguish between aldehydes and ketones. Now here one thing should be mentioned: aromatic aldehydes like benzaldehyde will reduce Tollens reagent but will not reduce Fehling solution. Now acetophenone and benzophenone. Acetophenone is C6H5COCH3. Now again here we have COCH3 group, so iodoform reaction, that is reaction with the iodine and NaOH, forming a yellow precipitate of CHI3, that is iodoform. Now due to the bulky nature of phenyl groups in benzophenone is this one. So space consuming or bulky phenyl groups are there, so nucleophilic attack is made impossible at the carbonyl carbon, and so benzophenone will not give a reddish brown precipitate with Borch's reagents, while acetophenone can give a reddish brown precipitate, red orange precipitate with the Borch's reagent, and Borch's reagent is 2,4-dinitrophenylhydrazine dissolved in methanol and acidified with the concentrated sulfuric acid. You take about 1 ml of Borch's reagent, add 1 or 2 drops of the ketone, and keep it in a boiling water bath. After 5 minutes you will get a red orange precipitate of 2,4-dinitrophenylhydrazone, and acetophenone can give such a reaction, while benzophenone, due to steric reasons, cannot give a red orange precipitate. And again acetophenone can give iodoform test, and benzophenone is a solid while acetophenone is a liquid. And there is a particular reaction of benzophenone which is very characteristic of benzophenone, that is, when benzophenone taken in ether is heated with a piece of metallic sodium, a blue or bluish green color develops. That is a specific test for benzophenone. Benzophenone is a white solid. When a piece of the solid is taken in a small test tube, and then you add some ether, and then you add a piece of sodium and heat it, so that you get a bluish green color, and this color is characteristic of benzophenone. So we can identify benzophenone by that test. Now there the bluish green color is due to some radical formation. The chemistry is complex. Now how will you distinguish between phenol and benzoic acid? Now there is one particular acid called carbonic acid, H2CO3. Now the acid strength of phenol, benzoic acid and carbonic acid is like this. Benzoic acid C6H5COOH is a stronger acid than carbonic acid, and phenol is a weaker acid than carbonic acid. So when you add sodium bicarbonate to benzoic acid. Usually a solution of sodium bicarbonate is taken and benzoic acid is a solid. You add a pinch of benzoic acid in the sodium bicarbonate solution. You will see bubbles of carbon dioxide coming up. It is called effervescence. So benzoic acid gives effervescence of carbon dioxide with the sodium bicarbonate solution, while phenol will not give this reaction because phenol is less acidic than carbonic acid, whereas benzoic acid is more acidic than carbonic acid. So benzoic acid can replace the carbonic acid from sodium bicarbonate, and carbonic acid easily decomposes to carbon dioxide and water, and this carbon dioxide is observed as effervescence. Now there is one specific test for phenol. It gives a violet color with neutral ferric chloride. Now ferric chloride is acidic because of hydrolysis, gives ferric hydroxide and HCl, hydrogen chloride, hydrochloric acid. You take solution of ferric chloride, it is yellow in color, a slight yellowish color for ferric chloride. You add ammonium hydroxide dropwise till the yellow color changes to pale green. We get a pale green coloration which indicates the solution is almost neutral. To this solution you add a drop of phenol or a solution of phenol made in water, and one drop is taken and added to this neutral ferric chloride solution. Immediately a violet color will be developed. This is a specific test for phenol. And so benzoic acid can be identified by, it is a solid, can be identified by effervescence of carbon dioxide with sodium bicarbonate solution, and phenol gives a violet color with a neutral ferric chloride. And again phenol can decolorize bromine water. Bromine water is brown in color, reddish brown in color due to presence of bromine. When bromine reacts from bromine water, the remaining liquid is water, so it is colorless, and a white precipitate of tribromophenol is formed with bromine water, and benzoic acid cannot give such a reaction. Then how will you distinguish between pentant 2-on and pentant 3-on? You write 5 carbon atoms in a chain, and on second carbon you collect double bond O. You write 5 carbon atoms in a chain, and on third carbon you write double bond O. And here for pendant 2-on there is the CH3CO group. So whenever there is CH3CO group or CH3CHOH group, such compounds can react with the iodine and alkali to give a yellow precipitate of iodoform CHI3. So pendant 2-on can give iodoform, while pendant 3-on cannot give iodoform. Now benzaldehyde and acetophenone. Benzaldehyde can reduce tolerance agents. I told you earlier that benzaldehyde cannot reduce filling solution. Benzaldehyde reduces tolerance reagent to metallic silver. We observe it as a silver mirror. And then for acetophenone there is one specific test, that is iodoform test. CH3CO group is present, so with iodine and alkali we get yellow precipitate of CHI3, that is iodoform, while benzaldehyde will not give iodoform. Then ethanol and propanol. Ethanol is acetaldehyde which contains the CH3CO group, so it can give iodoform reaction, while propanol cannot give iodoform with iodine and alkali. Then how will you prepare the following compounds starting from benzene? Metanitrobenzoic acid. You nitrate benzene and then treat it with methyl chloride and anhydrous aluminum chloride, that is Friedel-Crafts reaction. The nitro group, due to its minus M and minus I effect, will be producing positive charges at the ortho and para positions. So meta position is not made positive, so electron density in the meta position is higher compared to ortho and para, and so CS3 group, that is the electrophile CS3 positive, will enter the electron rich meta position, and we get metanitrotoluene. The compound is called metanitrotoluene, and on alkaline KMnO4 oxidation, the CS3 group is converted to COOH. Actually it is converted to COONA because permanganate is alkaline containing sodium hydroxide, and then on acidification, addition of H positive, we get COOH, metanitrobenzoic acid. Suppose we are starting with alkylation anhydrous aluminum chloride and CS3Cl first to get the CS3 group here instead of nitro group, then CS3 group is ortho-para directing, in the sense due to its hyperconjugation it will produce negative charges in the ortho and para position, so that further nitration will give ortho nitrotoluene and para nitrotoluene. So first attempts nitration and then attempts alkylation, that is Friedel-Crafts reaction. Now para nitrobenzaldehydes. Here the aim is to produce a methyl group on benzene nucleus, then nitrate it so that we get para nitro derivative, because methyl group, due to its hyperconjugation, increases the electron density in the ortho and para positions, and so methyl group is, we say, ortho para directing, and usually the para isomer predominates because of the steric interaction with methyl group. So we get para nitro compound, then you treat it with chromyl chlorides, CHROMYL, chromyl chloride. That is CrO2Cl2, and then acidified the resulting product, we get CHO group. That is, this reaction is known as Ethart's reaction, and again we can use chromium trioxide in acetic anhydride to effect the conversion of CS3 into CHO, chromium trioxide in acetic anhydride, CS3 CO CS3. This mixture can also oxidize this CS3 group to CHO group. So that is conversion of benzene into para nitrobenzaldehyde. How will you bring about the following conversions in not more than 2 steps? Propanone to propene. Propanone is CS3COCS3, that is acetone, and propene is this one. Now reduce the CO group to CHOH group using lithium aluminium hydride. Then dehydration reaction, 1H from here, and this OH is removed as a molecule of water. Using concentrated sulfuric acid at 443 Kelvin, we get propane. benzoic acid to benzaldehyde. The reaction is first reaction with PCl5, OH is replaced by Cl. Then hydrogen vanadium barium sulfate reduction. This is known as Clemenson's reduction. Rosenmund reduction. ROSENMUND, Rosenmund reduction. So all name reactions are important. There is Clemenson's reduction, which is reduction of aldehydes and ketones to the CO group is reduced to CS2 by zinc amalgam and HCl. So that is Clemenson's reduction. So hydrogen vanadium barium sulfate, this CCl bond breaks and 1H here and 1H here, CHO is formed. Now ethanol to 3-hydroxybutanol. Now first of all, ethanol is oxidized to an aldehyde using pyridinium chlorochromate. Pyridinium chlorochromate, that is reagent PYRIDINIUM CHLORO CHROMATE. So it's a combination of pyridine and hydrochloric acid and chromium trioxide, a complex compound formed between pyridine, HCl and CrO3. It is an oxidizing agent, a medium oxidizing agent we should say, because CS2OH is fully getting converted to CHO. Further oxidation of CHO to COOH is prevented. Now pyridinium chlorochromate we get CH3CHO, that is ethanol or acetaldehyde. Then with dilute alkali we get aldol condensation, aldol reaction, not condensation here, aldol reaction, because only addition reaction occurs. It is called a condensation when we heat the mixture. So CHO is converted to CHOH and 1H from this CH3 group is given for this oxygen of CHO to get CHOH, and then the remaining part CH2 CHO is getting connected to carbon, and this compound is 1, 2, 3, 4, 3-hydroxybutanaldehyde or butanol. Now benzene to metanitroacetophenone. Here also we can try first nitration and then Friedel-Crafts reaction. So nitration first, we get nitrobenzene and then subjected to Friedel-Crafts reaction using CH3COCl and anhydrous AlCl3. The COCH3 group is meta-directing because the bonds tend to move in this direction, so that positive charge is created at the ortho and para positions. So also nitro group is meta-directing, but nitro group contains more electronegative atoms, hence a higher extent of -I and -M effect, so higher deactivation of the ring, we say. A large amount of electron density is withdrawn from the ring system, so electrophilic substitution reaction is very difficult with the nitro group containing benzene ring. So it is best to start first with the acylation reaction, CH3COCl and anhydrous AlCl3 to give this compound. CH3CO group is connected. It is an electrophilic substitution reaction. We get acetophenone, then it is subjected to nitration using mixture of concentrated HNO3 and concentrated H2SO4. We get meta-nitroacetophenone because this group is meta-directing due to its -M effect. Of course, -I is also there. Benzaldehyde to benzophenone. Now for this reaction you should get phenyl magnesium bromide as the reagents, then CHO adding to phenyl magnesium bromide, this CO bond polarizes, and this MgBr positive is getting connected to oxygen, CO OMgBr, and this phenyl group is connected to CH, and on hydrolysis with water we get OH, and when this secondary alcohol is treated with copper at 300 degrees centigrade, 2 H atoms are removed, we get dehydrogenation reaction. It is called dehydrogenation. So removal of hydrogen, copper at 300 degrees Celsius, we get benzophenone. This compound is called benzophenone. Now benzaldehyde to 3-phenyl propanol. Again, benzaldehyde can condense with this acetaldehyde molecule. We can prevent condensation if we are not heating it, but when we are heating it, we are getting the condensation product, this oxygen atom combining with the 2 H atoms here, and we get CH double bond CH, CHO, and the whole compound can be reduced using hydrogen and palladium. This double bond will be reduced, the CHO will be reduced, CH2OH, and CH2 single bond CH2. So double bond reduction, CHO reduction using hydrogen and palladium. It is 1, 2, 3 phenyl propanol, bromobenzene to 1 phenyl ethanol. Now this is 1 to 1 phenyl ethanol. So ethanol CH3 CH2OH on one carbon 1, we have a phenyl group. Now this bromobenzene is treated with the magnesium in ether to prepare its Grignard reagents, and the Grignard reagent on reaction with an aldehyde other than formaldehyde gives a secondary alcohol. So MgBr phenyl magnesium bromide with acetaldehyde, we get MgBr connected to O, then phenyl connected to this carbon, and then on acidification O MgBr is converted to OH, we get this compound that is the same as this one. So that is 1 phenyl ethanol. Now I am stopping here. Thank you.